Assalamualaikum warahmatullahi wabarakatuh. In this presentation, we would like to elaborate and explain on the application of solving differential equations using eigenvalue problems in electrical circuit. This is member of the group. The first one, Azwa, Alia, NABILA binti NORAZLI. The second one, AQILAH binti SYAHARUL FITERI. And the third one is SITI SOFIYYAH binti ERWAN MURSHIDI. This presentation video contains 4 parts to be discussed, which are introduction, methodology, result and discussion, and lastly, the conclusion. So now, without further ado, we will proceed with the introduction to our project. Eigenvalues are used to determine the stability and behavior of linear time invariant systems such as electrical circuits. The stability concept is necessary for the dynamics of circuits. For stability, all eigenvalues of circuits must be located on the left-hand side of the complex S-plane. In general, the eigenvalues of circuits are obtained from the coefficient matrix relating to the state equations in the time domain in circuit analysis courses. The eigenvalues and eigenvectors of electrical networks can be used to determine the cause of an open or of a short circuit. It is crucial to comprehend both the momentary and steady-state reactions of circuits in the field of electrical engineering. We will discuss the importance of using eigenvalue problems as a powerful approach to solving differential equations, especially when dealing with linear time invariant LTI systems. Differential equations can be used to mathematically explain the dynamic behavior of linear time invariant LTI systems, which are frequently encountered in our work. Today, we emphasize on how these equations might be interpreted analytically using eigenvalue problems as a useful tool. In this project, we aim to offer an approach to the application of eigenvalue problems in the analysis and solution of differential equations in electrical circuits. Before we go deeper into the ODE method, let's briefly recap the basics of eigenvalue problems. Eigenvalue problems are a powerful tool in linear algebra often used to determine the natural frequencies and modes of a dynamic system. In electrical circuits, this translates into understanding the inherent oscillations and responses of the system. How does the ODE method fit into this picture? Ordinary differential equations, ODEs, serve as the mathematical backbone describing how circuit variables change with respect to time. In the context of eigenvalue problems, ODEs become a means to analyze the time evolution of the system, capturing momentary and steady-state responses. Firstly, transforming ODEs into matrix form. Having the ODEs in hand, the next step is to transform them into matrix form. This matrix representation is crucial as it allows us to leverage the power of linear algebra, setting the stage for the application of eigenvalue problems. Secondly, the eigenvalue approach to ODEs. Now, let's apply the eigenvalue approach to our ODEs. By representing the ODEs as matrices, we can derive the characteristic equation whose roots are the eigenvalues. These eigenvalues, in turn, unlock the inherent frequencies of the system. Next, eigenvectors and model matrix. Once we have determined the eigenvalues, the corresponding eigenvectors guide us in constructing the model matrix. This matrix, derived from the eigenvectors, plays a crucial role in expressing the general solution of the system. In addition, solving ODEs as the comprehensive approach. The effectiveness of the ODE method using eigenvalue problems lies in its ability to provide a comprehensive solution. With the model matrix in hand, we can express the complete system response incorporating initial conditions and external inputs.
As for the methodology that we choose ordinary differential equations, which is ODE, the electrical circuits composed of resistor, capacitors and inductor in the series. So the differential equations of the circuits is written as these equations. So where IT is the current that through the circuits as a function of time, R is the resistance, L is the inductance, C is the capacitance, and VT is the voltage applied to the circuits. Electrical circuits, whether simple or complex, are often described by differential equations. These components capture how currents and voltage change over time as various components interact. So to tackle these equations systematically, we need convert them into a matrix form because this allows us to apply linear algebra concepts and sets the stage for solving using eigenvalues problem. So for the next step is we need to formulate the characteristic equations. By finding the determinant of a matrix, subtract by a scalar times identity matrix, we can obtain the characteristic equations. The solution to the equations are the eigenvalues. So what I can say here, eigenvalues represent the natural frequencies of the circuits, while the corresponding eigenvectors provide us with information about the system response patterns. Together, they form a powerful pair in understanding the circuit's dynamics. The general solutions of the system can be expressed as a combination of the model matrix P constants derived from the initial conditions and exponential terms based on the eigenvalues. These solutions provide us a comprehensive understanding of the circuit's behavior over time. So to tackle this equation systematically, we need convert them into a matrix form because this allows us to apply linear algebra concepts and sets the stage for solving using eigenvalues problem. So for the next step is we need to formulate the characteristic equations. By finding the determinant of a matrix, subtract by a scalar times identity matrix, we can obtain the characteristic equations. The solution to the equations are the eigenvalues. So what I can say here, eigenvalues represent the natural frequencies of the circuits, while the corresponding eigenvectors provide us with information about the system response patterns. Together, they form a powerful pair in understanding the circuit's dynamics. The general solutions of the system can be expressed as a combination of the model matrix P constants derived from the initial conditions and exponential terms based on the eigenvalues. These solutions provide us a comprehensive understanding of the circuit's behavior over time.
Now, let's take a look at the result and discussion. The purpose of the implementation of ordinary differential equation is to solve the differential equation in electrical circuit. The first point is eigenvalues and natural frequencies. One of the key outcomes of our analysis is the determination of eigenvalues, each representing a natural frequency of the system. These frequencies are fundamental to understanding the dynamic behavior of our electrical circuit. The higher the eigenvalue, the higher the frequency at which the system naturally oscillates. Next is the model matrix interpretation. Moving on to the model matrix, it encapsulates the response pattern of our system. Each column of the model matrix corresponds to an eigenvector, indicating how each mode contributes to the overall system behavior. As we analyze these patterns, we gain valuable insights into how they. Furthermore is the impact of initial conditions. The influence of initial conditions on our system cannot be overlooked. By incorporating these conditions into our model matrix, we've been able to explore how the circuit responds to different starting points. This not only enriches our understanding of the system, but also allows us to predict its behavior under various scenarios. Next is the comparison with numerical solutions. To compare our analytical results with numerical solutions, numerical methods step provides a critical check on the accuracy of our method. While our analytical approach excels in providing insights, the comparison with numerical solutions help us refine our understanding and account for any difficulties that may arise in practical scenarios. Moving on to the real-world application insights, bringing theory into practice, we will apply our method to real-world circuits, whether it's analyzing the temporary behavior of a power distribution network or predicting the response of an electronic control system. The ODE method with eigenvalue problems proves to be versatile and invaluable. These insights directly impact circuit design and optimization in practical applications. Next is the sensitivity analysis. An intriguing aspect of our results is the sensitivity of the system to changes in circuit parameters. By exploring how variations in these parameters impact eigenvalues and consequently system dynamics, we gain a deeper understanding of the circuit's robustness and performance. This sensitivity analysis is crucial in the iterative process of circuit design. Last but not least is the limitations and future directions. As with any method, it's important to acknowledge its limitations. The ODE method with eigenvalue problems is powerful, but it may encounter challenges in certain scenarios. Looking ahead, we envision further research to refine and extend this approach. Exploring its limitations guides us toward a more comprehensive understanding of its applicability.
In a nutshell, the field of solving differential equations in electrical circuits using eigenvalue problems has eliminated the path to a deeper understanding of system dynamics. We have worked through the complexities of circuit modeling, matrix representation of equations, and the purpose of eigenvalues and eigenvectors. It becomes clear that eigenvalue problems provide more than simply mathematical solutions when we consider the gained insight. They operate as a link between the concrete reality of electrical system and the abstract realm realm of mathematics. An effective lens for analyzing and predicting dynamic behavior is provided to engineers and researchers by the capacity to extract a system's natural frequencies and modes.
That's all from us for this presentation. Thank you for your attention.